started in the earlier session, one of the earlier sessions where we did discuss about how chemical elements are formed in nature and how they react amongst themselves. So today's topic is an extension of that, where we will be exploring some aspects of how compounds are formed and how these compounds, there is a definiteness to how these compounds are formed, or and how we can predict what compounds are formed and so on. And then we will also touch upon classification of the elements as well as classification of these compounds based on some of their chemical properties and their availability in nature. So to start off, one question which most of you might already be knowing is how many elements do we have in nature?
118.
118 elements are the ones which are known to us, right?
Yes, sir.
These are known to mankind. But how many of them do occur in nature? How many of them are available in the universe around us, not created by us? They are not synthetic elements. How many are naturally occurring elements?
94.
Yeah, so this number of naturally occurring elements keeps sort of changing. When I was in school, that number used to be some 87 or 88. And what has happened is there are elements like plutonium and so on, which plutonium, neptunium, even technetium, which were synthesized first, but later found in the nature in very, very small quantities, extremely small quantities. So of the naturally occurring elements, there are 94 of them. Again, based on sources and how you define these naturally occurring elements, some books and websites might also give this number as 92. But if you go by the fact that even if they are found in extremely small quantities, if they can be found somewhere in nature, then you should go call it as naturally occurring elements. And there are few elements which are also naturally occurring and are also synthesized, right? So if you take the element like technetium or neptunium, plutonium, all these elements were first made by man and later they were also discovered in nature. Okay. Now, these 94 elements, how are they classified? How are they classified?
According to metals, non-metals, and metalloids.
Yeah. So first, classification is required so that we see some patterns in their properties, right? So based on that, one of the properties which in fact Lavoisier was the one who used it first, was classifying these elements and as metals and non-metals. And people found out that all elements can't be classified as metals and non-metals. So they created a separate category called metalloids. Now, can we put all the elements into just these three categories? Can we put all the elements into just these three categories? Yes. That depends on how you define a metal or a non-metal. So if I were to ask you, what is the definition of a metal? What do we refer to as a metal? Yes, anyone? What is a metal?
Any class of elements which have high electrical and thermal conductivity, as well as it has malleability, ductility, and high reflectivity.
Yeah. So let me use the keywords which you have used. You have spoken about conductivity. Conductivity, both thermal and electric. or electrical conductivity. Then you have spoken about malleability, ductility. What is malleability and ductility?
Malleability refers to the property of metals in which they can be converted into sheets, and ductility refers to the property of metal in which it can be converted into long wires.
Exactly. So malleability is the property of metals or elements where you can actually sort of hit them and make them into really thin sheets like foils, right? So metals have this great property of malleability, and ductility is the ability to draw very, very thin wires. Okay. The third property that you mentioned was, let me use a slightly more technical term. Call it as lustrous. Lustrous meaning it has a shiny surface. Okay. Now, do you think everything that is classified as a metal follows this breakup? Yes.
No,
Every
sir, there is some exception.
What are the exceptions then?
So, like in case of example, we can take that metals are mainly strong, malleable and ductile, but sodium metal and potassium metal, those two metals are not malleable or ductile or strong.
Yes. So for every case, whether it is conductivity, malleability, ductility, lustrous nature, or there is a general thinking that metals are very hard and so on, there are always exceptions. In fact, one of the first starting point is a lot of people mention that metals are all solids. Even there are exceptions. So with all these exceptions, this definition of metals, non-metals, and metalloids is not very accurate, or it is not very, you can say it is not universal. Okay. Now, another way of defining metals, non-metals, and metalloids is also deciding whether metals have basic properties, non-metals have acidic properties, and metalloids have amphoteric properties. What does this mean? Basic acid.
Amphoteric refers to the kind of the substance which can act both as acidic and basic.
Yes. So if you take a metal and a metal, when it reacts with oxygen, forms an oxide, and that oxide, when it reacts with water, it forms a base, which can then neutralize an acid. So metals have basic properties, non-metals have acidic properties, and similarly, metalloids have amphoteric properties, meaning they can exhibit both acidic as well as basic properties. Can you think of any exceptions here?
Aluminium.
What is the specialty of aluminum?
Aluminium acts as both basic and acidic. It is amphoteric. And also zinc.
Yeah. So aluminum acts as amphoteric because of two reasons. One is because it's a metal, meaning it has very few electrons in the valence shell, it has a tendency to give away those electrons. It has a tendency to leave those electrons. However, when it is leaving 3 electrons, it is a very small atom, no? So there is a high charge that is formed. So it cannot give away 3 electrons, though it intends to. At the same time, if you want to really pull out those 3 electrons, it takes quite some effort. So aluminum is one of those amphoteric elements where, though it intends to give away an electron, it is not able to. And at the same time, it also has a D shell, an energy level, D energy level, where it can actually accept electrons and form complexes. So in the case of aluminum, you will see sodium aluminate, some compound like that is formed, where it is actually an complex compound, or what we call as a coordination compound, right? Similarly, zinc has a tendency to give away electrons, And at the same time, it also has a tendency to accept more electrons to form complex or coordination compounds. That's why you see compounds like sodium zincate, which can also be formed, right? So they also have these acidic properties as well as basic properties. But when you take the definition of, let's say, malleability and ductility, both zinc and aluminum are malleable and ductile. If you take the definition of conductivity, both aluminum and zinc are have very good conductive properties. Are they lustrous? Yes, both of them are very lustrous. So if you observe, in terms of the other physical properties of conductivity, malleability, lustrous nature, sonorous nature, and so on, aluminum and zinc can be classified as metals. But if you go by how their chemical properties are, aluminum and zinc can actually be classified as amphoteric in nature. So there is always this conflict happening between how elements are classified. Okay. Now, similarly, you would expect non-metals to be classified as acidic in nature. Can you think of any exceptions there? Non-metals which are not acidic in nature.
Lithium.
Which one? I didn't get you.
Lithium.
Lithium is a metal and it is pretty base. It is actually basic in nature. Any non-metal which is not acidic in nature? One of the examples you can think of is boron. Boron is not, it's a very, very weak, it has very weak acidic properties. Another case that you can think of is all the inert gases. They don't have any chemical properties. So, meaning they don't, they are called inert because they can't react with other elements. So we are expecting acidic properties, but they have inert nature, or they don't react with any other elements. Okay, so all the noble gases, by this definition of expecting them to be acidic, they are not actually acidic in nature. Okay, similarly, another case is ammonia, nitrogen. Nitrogen forms ammonia, and ammonia is actually basic in nature. While another, like if you go slightly forward, fluorine reacts with hydrogen to form hydrofluoric acid. But nitrogen reacts with ammonia, reacts with hydrogen to form ammonia, which has basic properties. So when you take this definition of metals, non-metals, and metalloids, the classification is pretty confusing in nature. So you just have to know this, that there is no unique method of classifying. Okay. So which is the other way of classifying these elements other than metals, non-metals, and metalloids? Which is the other way of classifying these elements? Yes, in any other method of classifying these elements? Or any other method of arranging these elements?
Reactivity.
Reactivity, very good. Reactivity. So how would you arrange them, or how would you classify them?
High reactive to less reactive.
Yeah, so what you can do is you can arrange these elements as high reactivity to low reactivity. But what is your reference? Which element are you expecting them to react with? Which element are you expecting them to react with? Or which compound are you expecting them to react with? So whenever we talk about reactivity, usually what we do is we separate the reactivity of metals and non-metals. We observe the reactivity of metals separately. We observe the reactivity of non-metals separately. Okay. The reason being, when we are taking metals, we check their reactivity by making them react with an acid. And when we take the non-metals, we check their reactivity by making them react with either oxygen or hydrogen or a base also. Okay, so this is also another good way of arranging all the elements or classifying all the elements. And if you observe the reactivity series, especially among metals, we are very keen on trying to observe metals. So what are the most highly reactive elements that you can think of?
Potassium.
Yeah,
Sodium,
potassium, sodium, rubidium, cesium, they are highly reactive elements. And what are the lowest reactivity in terms of elements? In metals specifically.
gold, platinum,
Yeah, gold, platinum,
Silver.
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 Okay. What comes in between? Let's say roughly just above gold, silver, and
Hydrogen.
platinum.
Hydrogen.
Hydrogen, but because hydrogen is usually used as a reference, right? Hydrogen is not a metal per se. Hydrogen is used as a reference to compare with where these elements are. What about a which metals do you think will come next, just above gold, platinum, and silver?
Copper.
Yes, copper. What about just above that?
iron,
Iron, zinc.
Zinc.
Yeah.
Lead. Mercury.
lead,
Yeah, mercury is also, yeah, almost equally stable as iron or equally reactive as iron, right? What else? And just above this, you will see that calcium, magnesium,
Aluminum.
yeah,
Aluminum.
aluminum, they all fall in this category. Okay, so the reactivity is moving from very high reactivity to very low reactivity. And for reference, for the sake of reference, we include hydrogen here. Okay, but remember that hydrogen is actually not part of reactivity series of metals. So if you observe, everything else is a metal, only hydrogen is used as a non-metal for reference, just for the sake of comparison. Okay, next, what else? What is the other methods? What else can we use for classifying? Which are the other methods you can use for classifying? Or which are the other parameters you can use for classifying? Yeah. Yeah, Janvi has just messaged that you can arrange all of them according to mass number. So let me write it down according to atomic mass. So if you arrange them according to the atomic mass, what is the lowest mass number that you can think of?
Hydrogen.
Hydrogen. Yeah, what is its mass number?
1.
Yeah, one. Atomic number is also 1, mass number is also 1. And what comes next?
Helium.
helium,
Yeah, remember that hydrogen also has another variety. It is called deuterium, where it has mass number 2 and atomic number 1. Okay, hydrogen has another case where mass number is 3, atomic number is 1. Which means in the nucleus, in the first case, there is only one proton. In the second case, there is one proton, one neutron. And in the third case, there is one proton and 2 neutrons. These are what are called as isotopes. Basically, they have the same atomic number. Same atomic number means same number of protons and different mass number. meaning different number of neutrons. Okay, so remember that for the same element you can have multiple isotopes like this, right? What comes next?
Helium.
Yeah,
Lithium.
helium, what is the mass number?
4.
4.
Yeah, so the most commonly occurring one is helium-4. In fact, remember that there is also a helium isotope which has mass number 3 and so on. There are multiple cases. Okay, next comes lithium. Lithium, what is the mass number? 7,
7.
right? Next is beryllium.
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 Beryllium is 4, 8. Next,
Boron.
Boron.
slightly ahead, you will see that there is oxygen, right? Maybe slightly ahead, then what will you see? You will see sodium. Then slightly ahead, you will see iron. What is the atomic number of iron?
26.
26. Yeah, and most common mass number is 56. Right? Then can you think of tin? Tin, what is the mass atomic number of tin? It is mass number is 132, atomic number is 50. Then lead 82, 208. Remember that whatever isotope I am writing here, lithium, beryllium, oxygen, and whatever isotope I am writing here, it is just one of the several isotopes each of the atom will have. Understood? It is just one of the several isotopes that each of the atom will have. Now, the speciality of these isotopes is that they all have identical chemical properties. Why would they have the same chemical properties? Why would they have the same chemical properties? All isotopes.
Because they have same atomic number.
They have same atomic number.
Yeah, so the reason you should be giving is chemical properties depends on electronic configuration, or chemical properties depend on the way the electrons are arranged in the shells. Okay, but in the case of isotopes, what is changing is only the nucleus, but nothing is changing with respect to the arrangement of electrons or electronic configuration. So that is the reason all isotopes of a particular element does not mean that helium and hydrogen will have same chemical properties. All isotopes of a particular element will have the exact similar chemical properties. However, their physical properties like mass itself is very different. Okay. You should also remember they have different nuclear properties, because nuclear properties are dependent on the nucleus. Because nuclear properties are dependent on the structure of the nucleus, for all isotopes, the nuclei are changing. So automatically nuclear properties will keep changing. Okay, any questions at this point?
No, sir.
Okay. So any idea about which element has the maximum number of isotopes? Which element has the maximum number of known isotopes?
Carbon.
Okay, what are the elements that you, what are the isotopes that you know for carbon?
It's
C12,
green
13, C12, 14.
diamond.
Yeah, the names that you had given as diamond, graphite, and so on are what are called as allotropes. They are not isotopes. Allotropes mean how the elements atoms are arranged. There is no change in how the nuclei are arranged. Allotropes only means, or is a study about allotropy, is basically a phenomenon where different types of physical properties are exhibited by the same element because of the difference in the arrangement of the atoms. Allotropy is different. Isotopes, on the contrary, have,
So may I name
yes,
carbon 12, carbon 13, and carbon 14?
yeah, carbon 12, carbon 13, and carbon 14 are the three known allotropes of carbon. Amongst the elements which have maximum number of isotopes is tin. Here, tin, which has an atomic number of 50. It is known to have about nearly 30 different isotopes. Okay, and it does not mean that all the isotopes are stable. Once you have an isotope, there is a high tendency that this isotope would want to change into something else, something which is more stable. So isotopes actually participate in nuclear reactions. There are usually only one or two stable isotopes. Okay, so which is the heaviest isotope that is available in nature? Which is the heaviest isotope that is available in nature?
Lead,
Yeah, so lead, which has atomic number of 82 and mass number of 208, is amongst the heaviest stable isotopes. It will not have any tendency to change further. So lead has amongst the highest stable isotopes, or the heaviest stable isotopes. But the heaviest isotope seen in nature, and it is actually present in significant quantities, is uranium-238. Uranium-238. Now this uranium-238, any idea how big or small it would be when you compare it with hydrogen? Uranium-238, how big or how small would it be when you compare it with hydrogen? So remember that there is one simple formula that gives an approximate, that gives us an approximate size estimate of atoms and nuclei. So for nuclei, this is R into R naught into A power 1, A power 1 by 3. Okay, R naught is the radius of hydrogen nuclei, and it is in the order of Fermi. Fermi means 10 power minus 15 meters. And A power 1 by 3 means it is a cube root of atomic mass, cube root of the mass number that we have seen. So this simple relationship will give us a comparison between different sizes of atomic nuclei. Okay, but the atomic radius of any atom, this is nuclear radius. The atomic radius of any atom is approximately equal to or in the order of few nanometers. angstroms. That is 10 power minus 9 meters or 10 power minus 10 meters, which means compared to the radius of a nuclei, the atomic radius is about 10,000 times, at least 10,000 times bigger. Okay, so even if you arrange all the nuclei together one after the other along the diameter of a atom, it will require at least 10,000 different nuclei to arrange them. Okay. I have received a message from JNV Porbandar that cesium and xenon have 36 isotopes. Yes, you are right. The many of them are actually unstable. So in terms of the most number of isotopes observed in nature, and with many of them actually being stable, the number is actually 10. Okay. The next part, or can you think of the next property based on which you can classify elements? How can elements be classified? We have so far looked at calling them or classifying them using metals as non-metals or metalloids. Then there is a chance to classify them based on reactivity. Now we have looked at how we can classify them based on atomic mass. What is the other way of classifying them?
Atomic numbers.
Atomic number is 1. Okay, great. So how do we classify them based on atomic number?
Isobars.
Yeah, isobars are not really important at this point, but still, how do we classify them based on atomic number? See, the logic is very simple here. If you go back and observe, the atom or the element is changing only when the chemical properties are changing, or the element is changing only when the atomic number is changing. Or you can also say the element is changing only when the number of protons inside the nucleus is changing. Once the number of protons inside the nuclei are fixed, they will have the same chemical properties. They will not change from one to the other. Okay, so atomic number is an excellent method of classifying all the elements. You can actually arrange them in an increasing order of atomic number, right? So if you start, hydrogen has atomic number 1, helium has atomic number 2, lithium has atomic number 3, all the way till the last atomic number, that is, let's call this element as X. This has an atomic number of 118. Okay. Is there any element between these 118 elements where this atomic number is empty? Is there any element where the atomic number is empty? In reality, none. Some time ago, people believed that atomic number 43 was empty. That was technetium, which was later synthesized. There were other atomic numbers beyond 94, 95 onwards, which were synthesized. Otherwise, they were also empty. But today, all atomic numbers between 1 to 118 have been discovered. Okay. Now, the moment you put them in some increasing order of atomic numbers, what is the use? What is the use in just arranging them according to the number? It will just form a very long sequence of elements, no? Can we arrange them better in a better manner? Yes, can we arrange these elements in a better manner instead of writing down as a long list of elements? This is where scientists came up with periodic classification. So when scientists were actually arranging these elements, according to the elements that they have discovered, either according to their atomic mass or according to their atomic number or according to their chemical property, they observed what is called as periodicity. What is periodicity? It is a periodic repetition of properties. So after every 8 elements, or after every 10 elements, after every 18 elements, there is a repetition of properties that keeps happening in the periodic table. Okay. Now, what people have now done is, whenever there is periodicity, they have started putting them together in a tabular form, saying that everything that comes together will have the same set of chemical properties. So this is how a periodic table will look like, where all these elements which are actually coming together will have the same set of chemical properties. Okay. Now this periodic table, you might be knowing, is actually divided into several columns like this, How many columns are there in the periodic table? Yes, how many columns are there in the periodic table?
18.
Yeah, so there are 18 different columns. And these 18 columns are called as groups. Okay, so these groups have similar chemical properties. Sorry, there was some network drop. Yeah, so when we have these 18 columns, these 18 columns are called as groups and they have similar chemical properties. For example, all the inert gases that you know, they all form in one vertical column. They are all called as inert gases. They don't react and they are all clubbed together as one group. Similarly, sodium, potassium, rubidium, cesium, they are all very highly reactive elements. They are all clubbed together as one group. Okay, next, beryllium, calcium, magnesium, they all behave similarly, so they are all clubbed together on one group. Okay, so you can, these groups have different names. For example, this group which has lithium, sodium, and so on, this group is called as alkali metals. Alkali metals because they form alkalis and they are actually all metals. Okay. The group which is adjacent to it, which has beryllium, magnesium, and so on, this group is called as alkaline earth metals. Alkaline earth metals. The last group is helium, argon, krypton, xenon, radon, right? And I missed neon here. Helium, neon, argon, krypton. These are all inert gases, or they are also called noble gases. Right? Immediately next to them, there is fluorine, chlorine, bromine, iodine, and statine, and so on. These are called as halogens. Okay. Immediately next to them, from the right side, there is oxygen, sulfur, tellurium, and so on. What are these elements called as? Oxygen family. It has another name. It is called as chalcogens. Okay. Next to it is nitrogen family. So usually, if they don't have any special name, they are called as the family of the first element. So there is boron, the first element here. So everything else is called as boron family. If there is carbon here, everything else is called carbon family. There is nitrogen here, so everything else is called nitrogen family, and so on. Now in this table, if you observe, these are all metals, and on this side, they are mostly non-metals. Am I right?
Yes, sir.
On the left side, they are all metals, and on the right side, they are all mostly non-metals. So this bunch of elements which are there in between, they are called as transition elements, because there is a transition happening from metals to non-metals, and all these transition elements are also metals. So all your iron, zinc, cobalt, mercury, copper, gold, platinum, all of them are present in these transition elements. Okay. Now there is a separate box here, right at the bottom. What is this?
Lanthanides and actinides.
Lanthanides and actinides. So the first one is called lanthanides. They are called lanthanides because they follow the element lanthanum. And the second one is called actinides because they follow the element actinium. Okay. But together, what are they called as? Together, these are called as inner transition metals or inner transition elements. The reason these are called as inner transition elements is actually these should have come here. This was the space for these elements. But if you insert them here, the periodic table will become extremely long like this. It will become very flat and long. So instead of extending the periodic table like this, we are sort of keeping it compact. And because these were supposed to be inside the transition elements, these are called as inner transition elements. Okay, any questions here? These are called as inner transition elements. Okay, now another interesting property that you can observe here is when you are arranging the electrons, the left side of the periodic table, is ready. All those elements are ready to give away an electron. They are ready to take positive charge. So they have high electropositivity on this side, right? So electropositivity actually is increasing towards the left, and it is also increasing towards the downwards part of the periodic table. Okay, so the most electropositive elements will be here in the periodic table. The most electropositive elements will be at the bottom left corner. They are so big, the atoms are so big that they can easily give away an electron. Okay, now similarly, if you take this corner, there is a tendency to take electrons. And that tendency to take electrons is called as
Negativity.
negativity. So the tendency to absorb electrons is called electronegativity. So the most electronegative elements are in this corner of the periodic table. Why am I dropping the inert gases out? Why am I keeping the inert gases out?
Because they don't have valence electrons.
Yeah, so because they already have their outermost shells filled, they do not have a tendency to donate or absorb electrons. So though they are the last column on the right side, they actually don't have much of chemical properties, so we don't study them much. Okay, next. So if I ask you, how is the electropositivity changing along the period? What are periods? Periods are these horizontal rows. Okay, periods are horizontal rows, and there are 7 periods in the periodic table. Okay, so the periodic table has 7 horizontal rows. These two, lanthanides and actinides, are considered part of row number 6 and 7. Okay, so they are considered part of 6th and 7th period. Okay, so now my question, if you are moving along a period, if you are moving left to right, is the electropositivity decreasing or increasing?
Decreasing.
It is decreasing. Very good.
Decreasing.
If we are moving from left to right in the periodic table, is the electronegativity increasing or decreasing?
Increasing.
It is increasing. Very good. So if you are going along a group from top to bottom, is the electropositivity increasing or decreasing?
Increasing.
It is increasing. Okay. If you are going from bottom to top, is the electronegativity increasing or decreasing?
Increasing.
Increasing.
It is increasing, right? If you consider the green color that I have shown, electronegativity increases as you go from bottom to top. So there might be questions around this in the NTSC as well, where they'll ask, how are these elements arranged in the periodic table? What is happening to the properties? There could also be questions like, what is happening to the size of an atom? I will not go into all these details in this class because we have limited time, but you can actually refer to some good books where they would explain all of these in great detail. Okay. The reason this is called as a periodic table is because there is a periodicity, there is a repetition of properties of elements in this. And a lot of scientists have actually spent great amount of time understanding or coming up with different patterns of how we can arrange these elements. Any questions at this point? Okay, if there are no questions, I'll quickly move to the next topic and a short topic of today's class. We had last time, we did discuss about compounds, right? What are compounds? Yes, what are compounds? Compounds are combinations of atoms where there is a definite proportion, right? Every molecule is identical where there is a definite proportion of elements which are participating. Okay, now whenever you're looking at compounds, remember that compounds have unique chemical properties. Unlike in mixtures, when you separate these two components, they have different chemical properties. But in a compound, as long as you don't break that molecule, they have very unique chemical properties. Now, one way of classifying these compounds is to classify them as acids, bases, and salts. Acids, bases, and salts. So how are they different, acids, bases, and salts? Or what are acids, bases, and salts? How would you define them?
Acids are source.
Yeah, so one way, see, just as we had described these elements by physical properties, conductivity, malleability, ductility, and all. Similarly, you can define acids and bases as based on their physical properties. One bases, for example, have a soapy touch, right? Acids are sour, and so on. So one way is you can define them by their taste. You can also define by their soapy touch, how they feel in hand. So these are all called physical properties. But what about their chemical properties? How do acids behave when in the presence of other chemicals?
They are basic.
Yes, Shika, go ahead.
According to their presence of hydrogen ions and pH.
Yeah. So there are 2-3 ways of defining this. There is no unique way. So there were multiple scientists who came up with this, trying to give an accurate definition of what are acids, bases, and salts. One of them was, for example, Arrhenius came up with this theory saying that acids can produce H+ ions. Okay, and bases can produce OH- ions.
So in their aqueous solution.
Yeah, in an aqueous solution, the moment you mix them in water, acids can produce H+ ions and bases can produce OH- ions. This is one type of definition. And chemicals which are formed by combinations of these acids and bases are defined as salts, right? So this was a theory of Arrhenius. Now, people found out that this was not always true. In all cases, there were not OH- ions were not being produced. So they said acids can produce H+ ions and bases can absorb H+ ions. Acids can produce H+ ions and bases can absorb H+ ions. So this was an acid-base theory which was given by Bronsted and Lowry, two chemists who came up with this theory. Now people found out that as they discovered more and more chemicals, they couldn't define this also, or they couldn't classify this also. Like for example, by if you in the first case, if you had HCl, when it reacts with NaOH, it forms NaCl and H2O. This is a very, very simple, straightforward acid-base reaction, right? So this is acid, this is a base. You can see that in the acid, the H+ ion is coming out. You can see that the OH- ion is coming out. A salt is formed and water is separated. This is based on the Arrhenius theory. Okay. Now, another interesting theory, for example, is, let's say you have HCl reacting with ammonia. You would have done this reaction or experiment where you take a small tube. On one side, you keep a bit of cotton, which is wetted in dilute hydrochloric acid. On the other side, you take some ammonia, a cotton piece, a swab, which is wetted in ammonia. Put them, you will see that the vapors are actually interacting with each other, and roughly at the center of the tube, you will see some white fumes being formed. Those white fumes are from ammonium chloride. So here, HCl is an acid which is giving out as a H+ ion. Ammonia is not producing OH- ions, but ammonia is a base because it is taking this H+ ion and it is forming NH4 plus and Cl minus. And this is a salt. Okay. Now people figured out that even this was not an accurate definition. So they came up, Lewis came up with this theory saying that an acid can take a lone pair of electrons while a base can donate a lone pair of electrons. So if there is a pair of electrons, right? If, let's say, if you then an acid can donate a lone pair of electrons, a base can take a lone pair of electrons. Now, the same example of what you are seeing here can actually be explained using that, right? So even if you were to use another example, let's say you have let me take the example of, yeah, AlCl3. When it reacts with a very strong base, like let's say NaCl, right? There is a complex AlCl4 which is formed, and NaCl is there. Now, what does this mean? Here, chlorine has multiple lone pairs of electrons. So, chlorine has a tendency to give one lone pair of electron to this Al here, and this aluminum has a tendency of absorbing the lone pair of electrons because it has empty shells, right? So here AlCl3, though we are expecting it to be a salt, actually behaves like a Lewis acid. Okay, so this definition of lone pair of electrons might get confusing at school level. You need not worry too much about it. But what you have to remember with respect to defining an acid or a base are these two theories of either have the ability to produce H plus ions, that is an acid. A base either has an ability to absorb OH minus ions or absorb H plus ions or produce OH minus ions. Okay, so this is one way of classifying all these elements, and compounds which are formed by combinations of these acids and salts, acids and bases are called as salts. Okay, now in salts also, there are what are called as simple salts. So most of the salts that you see around yourself, CaCl, NaCl, CaCO3, Na2SO4, Na2CO3, let's say NaHCO3, right? All of them are simple salts. And why are they simple? They are made of two pieces. One is coming from a base, CaOH taken twice, and the other is coming from an acid, H2CO3, carbonic acid. Similarly, Na is coming from NaOH, HCO3 is coming from H2CO3. One component is coming from an acid, one component is coming from a base. When they react or when they merge together, you get simple salts. The other variety of salts are called as complex salts. Complex salts, or they are also called as coordination compounds. Okay. Now, for example, you have potassium ferrocyanide, FeCN6. See, if you break this, you will get 4 K plus ions and one complex like this. I'm sorry, 4 plus, 4 minus. Sorry. One complex like this. Now you will see that this is not coming from not from any particular acid, right? This itself is a combination of multiple components. That's why this is called as a coordination compound. Okay. Most cases, coordination compounds are formed around elements which are from transition elements. In the periodic table, we mentioned this area as the transition elements. So these transition elements and inner transition elements have the ability to form coordination compounds. And usually, coordination compounds are very colorful. They have colors. But the simple salts don't have colors. Like you can look at calcium carbonate, white in color. So baking soda, white in color. Washing soda, white in color. Sodium chloride, white in color. Everything is almost always colorless or white in color, right? But coordination salts, for example, think of coordination compounds. Copper sulfate with 5H2O, it is blue in color, right? Ferric chloride, brown in color. Potassium ferrocyanide, because of the ferro component there, it has a greenish tinge to it. Cobalt salts usually have blue color. Manganese salts have purple color. Potassium permanganate is KMnO4. Is also a complex salt. Potassium dichromate K2Cr2O7. It is also a complex salt. Potassium permanganate has a purple color. Potassium dichromate has an orange color. So salts also are two types. Okay. Salts which can be found from simple acids and bases are called as simple salts. Salts which are formed by ligands, these components, extra components which are there are called ligands. And they are not directly from any acid. They don't come from, like for example, this component, this manganate part or this dichromate part is not coming from any acid. It is formed in that when the reaction is happening, this complex ion is formed. Right? Such salts.
Excuse me, sir.
Yes.
So actually, I wanted to ask something, that if we talk about amphoteric oxides like aluminium oxide and zinc oxide, if we measure them with litmus or any pH, so what will be their value?
Yeah. So if you take, for example, zinc hydroxide. Zinc is actually has basic nature, right? So zinc hydroxide, if you measure the pH value, it will be greater than 7. Similarly, aluminum hydroxide, pH will be greater than 7. They will have basic properties only. What happens is, in the presence of a stronger base, for example, Al2O3, when it is reacting with sodium hydroxide, this is a weak base. This is a strong base. So in the presence of a strong base, then this starts behaving like an acid. Not that it is exactly an acid, but it behaves like an acid. That's why it has amphoteric properties. Similarly, ZNO is a weak base. It has it is a base. It has pH value above 7. But in the presence of a very strong base, let's say potassium hydroxide, it will start behaving like an acid. It has amphoteric properties. Okay, by itself, it will not behave like an acid. In the presence of a very strong base, it will start behaving like an acid. In the presence of an acid, both aluminum oxide and zinc oxide will behave like bases only. Okay, Have I answered your question?
Yes, sir. Yes, sir.
Okay, great. So the last component is, remember that from now on, whenever you are told about a salt, the first thing that you should think about, is this a simple salt or a complex salt? A simple salt in all likelihood will not have any color. There are exceptions, 1 or 2 exceptions here and there, but most simple salts do not have colors. And most complex salts definitely have colors. So whenever you are seeing a colored chemical in your chemistry lab, you from now on, you should be able to separate them. What is a simple salt and what is a complex salt? So I'll stop here. There is another small component for which we don't have enough time today. Maybe we'll take it up in the next class. Over to you.
Thank you, Praveen sir. I believe everyone in the class had a good participation today. We all interacted and we all understood this, slightly confusing topic. Like the elements and the periodic table itself can be very overwhelming, I would say, even for class 11 and 12 students. And